Geeta ma'am, can we start now?
We can start.
Okay, so good afternoon all.
1 minute, Kalpesh. She is going to introduce you. She is going to start.
Yeah, sorry.
So, hello and good afternoon to one and all present here. I am Kashvi Pota, Events Co-Head of BMSA, your host for today's session. I welcome you all again to our series of workshops and webinar that is BMESI sponsored certification course in medical devices, manufacturing and regulations organized by Biomedical Engineering Department of VIT. After the phenomenal success of our first event, we are all set for yet another remarkable event where we get the opportunity to learn and expand our knowledge. On behalf of BMESI and BMSA BIT, I take this opportunity to welcome you all for the second event, which is hands-on workshop on AI and ML in healthcare system by Mr. Kalpesh Patil sir. Before I go ahead, here are a few instructions for all our participants. Please keep your mic on mute for smooth functioning. Also requesting you all to note down your queries in the chat box or WhatsApp groups. We will be addressing them at the end of the session. This event will also be live streaming on YouTube. I would request you all to fill the feedback form at the end of the session in order to avail the certificate. If you find any difficulty joining the meet, please join us on YouTube. The link for all the above will be provided in the chat section as well as on the WhatsApp group. I would now like to give a brief introduction of our eminent speaker, Mr. Kalpesh Patil. He is an alumnus of VIT and a data scientist with great interest in AI research and innovation. Since last 6 years, he is working as a data scientist and has developed machine learning.
Kashvi, you're on mute.
I'm so sorry. Give me a minute. Hello and good morning to one and all present here. I am Kashvi Pota, Events Co-Head of BMSA, your host for today's session. I welcome you all again to our series of workshops and webinar that is BMESI sponsored certification course in medical devices, manufacturing and regulations organized by Biomedical Engineering Department of VIT. After the phenomenal success of our first event, we are all set for yet another remarkable event where we get the opportunity to learn and expand our knowledge. On behalf of BMESI and BMSA VIT, I take this opportunity to welcome you all for the second event, which is hands-on workshop on AI and ML in healthcare system by Mr. Kalpesh Patil sir. Before I go ahead, here are few instructions for all the participants. Please keep your mics on mute for smooth functioning. Also requesting you all to note down your queries in the chat box or WhatsApp group. We will be addressing them at the end of the session. This event will also be live streaming on YouTube. I would request you all to fill the feedback form at the end of the session in order to avail the certificates. If you find any difficulty joining the meet, please join us on YouTube. The link for all the above will be provided in the chat section as well as the WhatsApp group. I would now like to give a brief introduction of our eminent guest speaker, Mr. Kalpesh Patil. He is an alumnus of VIT and a data scientist with great interest in AI research and innovation. Since last 6 years, he is working as a data scientist and has developed machine learning and deep learning algorithms for healthcare and fitness domain. He has worked on image stitching, object detection, and image segmentation models to count and classify different types of cells and identify abnormalities. Without further ado, I would now like to invite Mr. Kalpesh Patil sir to continue higher. Over to you, sir.
Yeah, good afternoon everyone. So today's session is all about artificial intelligence applications into the field of healthcare. So there are many possible, I guess I'm not able to change the slide. Hello.
Yes, sir.
I guess I'm not unable to change my slide. I guess.
Your screen is visible.
Okay.
Yeah.
Fine. So artificial intelligence is used in major like three case scenarios in the healthcare system, like diagnosis, prognosis, and treatment. So diagnosis itself is a broad subject that we'll be looking to today. And in layman terms, if you define like what is an artificial intelligence, it is like a giving an ability to a machine for performing a task that actually reduces human efforts. And how we can do that is using programming techniques and tools that will automate the machines, that will incorporate the various systems and cloud architecture to implement the same. So if you consider the healthcare scenario, there are three major applications. Those are diagnosis, prognosis, and treatment. So diagnosis, there are lots of example into it, like tumor detection from MRI images, arrhythmia detection from ECG. Similarly, prognosis, once you done and one kind of a diagnosis, and based on your result of diagnosis, we can further estimate the possible of any disease with the estimation of time for the same. So like forecasting the risk of lung cancer, recurrence after the therapy, this thing can be possible with the medical prognosis. And the treatment, where estimating the effect of the treatment of the specific drug given to the patient. So here we'll broadly discuss about the medical diagnosis, uses of AI into the medical diagnosis. So there are lots of use cases in for the medical diagnosis. So we'll look one by one example. So one of the example is tumor detection from a whole slide image. So whole slide image, which is used in digital pathology, where you can have histopathology, cytology slides, and those slides are captured and and very high resolution image, which is can be in like 50 by 50 50K by 50K pixel resolution images can be captured, and those images are further uh, captured with the varying magnification, the magnification of 40x or 100x, and those high resolution images are used for the identifications of various kind of tumors in it. So this is the normal uh, flow how by which it works. So we capture the whole slide image from the automated microscope, where automated microscope captures images with the very high magnification, 40x or up to 100x, and those images are stitched together to form a single image of a very high resolution. And those images are further trained by different techniques. Patching is one of the technique where again those high resolution images are converted into small patches, and those small patches are annotated by the pathologist. So annotation is kind of a labeling where pathologists can label that this is a particular kind of tumor. So those images are given to the deep learning algorithms. So deep learning algorithm will be trained, and in the next event where you can pass only a raw image to the system, it can automatically identify the tumor present in it. So we'll discuss how this can be achieved in the subsequent slides. Again, another example is pneumonia detection from chest X-ray, and where you can have the chest X-ray images, and you can again same thing is carrying out here for the every uh, medical imaging application with the deep learning technique. You need to have some kind of a data set first, and on that data set you have to do image annotation, where you annotation that is labeling the particular section of an image, where you can highlight particular section from the image and can label it whether that's the abnormal case or not. And based on those kind of data set, again your system will learn and can automatically identify the abnormalities by its own. Another is the brain tumor detection from the MRI images. So again, only your raw image may not give you desired result every time. So you have to do some kind of pre-processing onto the image before applying to your model. So yeah, so this is one of the example where we take brain MRI image, perform some sort of image pre-processing, and those image after that pre-processed image is given to the CNN model, that is a convolution neural network model, and that model can predict the tumor as well as can estimate the position of the tumor as well. So we'll see that in later section. This is another example, the detection of resins in mammograph. So we take an image, and there are different the medical imaging techniques by which you can perform this. So this is one of the technique where the object detection method is utilized, which is based on again convolution neural network, where you have identified the location as well as you classify those identified object. So it's a two-stage process where you identify the location of the object, and you then further classify that identified objects. So this is again one of the example where the CNN model is used for the identification of detect intelligence. Again, apart from medical imaging, AI is also used into the physiological signals analysis, and the best known cases are like ECG, EMG, and EEG, as well as PPG, where you can uh, take a raw signal, can perform some sort of pre-processing, that is a signal denoising, and then further do some kind of feature extraction over it. And based on those feature, you can able to predict different parameters. So maybe you can estimate the type of ECG, type of arrhythmia you have. So from the EEG, you can also estimate what kind of emotion or what kind of a mood that particular person is. So those things can be possible from the various physiological signals. So one use case is arrhythmia detection from the ECG, where we take raw ECG signal, perform pre-processing over it, then we do segmentation. It is basically eliminating the noise and taking only desired part, and we perform feature extraction. Feature extraction is like identifying the key points or key information from your raw data, and the feature extraction is something from which your model will learn. So that takes lots of times and effort for the feature extraction, but this is a conventional machine learning technique where you take a raw signal from the image, perform some kind of pre-processing, signal denoising, and identify various features into time, frequency, and a wavelength domain. And based on those features, you train your machine learning model. It may be tree-based algorithm, like random forest, XGBoost, or maybe support vector machines. This is a name. Don't worry if you can't get anything from these numbers, but these names. But there's a conventional machine learning techniques where you get how to identify certain features, and those features are used to training those models and further classifying into different type of arrhythmia. Alternative to this, you can use deep neural network or artificial neural network with a very high uh, hidden neural layers in it. So those where feature extraction processes happen by network architecture itself. So you need not to manually identify or extract the features. So your model will itself identify feature and will select the best features out of it, and it can classify. So in that case, you just need to provide raw data into it. Yeah, again, it's not that simple, but it's like you not to do any kind of a pre-processing, any kind of feature extraction or it pre-processing is required. Uh, but feature extraction can be done by your model itself. But catch is that uh, when you have limited kind of a data set, in that case, your deep learning model won't work that well. So conventional machine learning techniques are normally used in such a cases where you have limited data set. So again, this is one of the use case. The predicting emotional state from EEG where you take a raw EEG signal, then you do filtering like a denoising, then again feature extraction and classify. So in most of your cases, where if you are collecting data by your own, let's say in your any project, you don't have any available data set with you, and in limited time you want to gather a data set and then create a model out of it. In that case, machine learning, conventional. Uh, Anyone was saying something?
No, sir, you can.
Yeah.
Kalpesh, please carry on.
Okay. So let's say you have a very limited time span and you don't have any available data with you, and you wanted to gather data by your own. So let's say you have designed and EEG capturing EEG signal capturing machine, maybe head cap or something like that, and you wanted to identify uh, the subject's emotions, like whether he's an angry, happy, sad, or whatever. So what you will do is you will gather a data with your machine, and those data obviously will gather as you will be having one or two machines developed by you for gathering the particular data. So data sample will be very less. So in that case, you can opt for a conventional machine learning algorithms. What I mean by conventional machine learning algorithms are, those are not ANN models. So other than ANN models, which are like a support vector machines or tree-based algorithms like random forest and boosted trees, XGBoost and all. So this can be utilized by you. So, but here you have to identify various features out of it, and those features you have to fit to a classifier, and that classifier can further classify into various states. So again, from your physiological signals, you can extract or evaluate different kind of parameters out of it. So nowadays you can see in your Apple Watch or in a Samsung Galaxy Watch, they provided you their ECG sensor as well, and there's an option to have an BP measurement as well. So we'll look like how you can use like ECG or a PPG signal to estimate different parameters. Again, here the uh, machine learning and deep learning technique will come to your help, where you can use the raw signal data and then uh, perform various feature extractions. Or if you go with a deep learning technique, you can tune your deep learning model to identify or to estimate the parameter. In this case, estimating the uh, blood pressure value. So this is again the one of the use case. Yeah. So when we talk about physiological signals, so you guys must be aware that like when we capture any physiological signal, you get more noise than a signal. So EMG is a worst case scenario, but in ECG again you get lots of noise along with your signal. There are many reasons for that. Due maybe the improper placement of your sensors, maybe your the ECG amplifier circuit design is not that great, or maybe you have not considered uh, the possible noises which are coming from the environment as well. So there's no kind of a proper shielding or something like that. So there are so many cases. It goes signal processing happens at every level. So first is when you design your amplifier, you take care that you will take only those kind of components from your signal which is required. So in case of ECG signal, let's say your normal signal frequency is from 0.1 hertz to 120 hertz. So you can design an amplifier with your the high pass band pass filter with the which will pass only zero point 0.1 hertz and 120 hertz. So you will have a low pass filter at the cutoff of 120. So it will pass only those signal which is below 120, and a high pass at cutoff 0.1. So it can pass signal above 0.1 only. In that case, so what will happen is whatever the signal below 0.1 and whatever the signal above 120 is eliminated. But what about signal in between 0.1 and 120 hertz? it's not always that you will get only pure signal in zero point 0.1 hertz and 50 or zero point 0.1 hertz and 120 hertz, because there are other noises as well within that same frequency range. So one kind of a noise is which are coming from your power source, which is normal 50 hertz noise signal. So that 50 hertz noise we normally use notch kind of filter, but that's not a good way of dealing with it, because 50 hertz is again the dominant part of your signal, and applying a notch is actually will result into loss of your data as well. So we do some in such a cases we apply wavelet based denoising technique, where we we denoise the signal by using one sort of you can say discrete wavelet transform. So we convert your signal into the DWT signal with the help of certain kind of those are called as a mother wavelets. So there is a different series of wavelets, Dobby cheese and Har. Har is a very simple kind of. So in one of the example, we'll take how we can do we can use wavelet based denoising technique to eliminate the noises. So again, time domain analysis, frequency domain analysis are working along with the wavelet based analysis to extract the different kind of features. Wavelet and frequency based analysis again can be used for your signal denoising as well. So signal processing is again very important part, because if your signal or your data is improper, in that case, whatever the best machine learning algorithm if you apply, it won't give you result. So so data is also very important part of it, and in our case as well, like most of the efforts are given to gather very uh, good quality or very clean data and perform various kind of pre-processing to uh, get the data so that we can so that machine learning or deep learning algorithm can extract maximum out of it. So yeah, so signal processing is equally important, and we'll look some of the example where using different signal processing techniques how we can extract information. So this is what I was talking about, wavelet based denoising. So wavelet will help you where you can use a wavelet where you can't apply like even after applying high pass and low pass filter, your noise is uh, frequency of your noise signal and frequency of your physiological signal is within the same range. In such a cases, you use wavelet based denoising. So we'll take an example and can go into detail of it later. So yeah, this is the how it has been done. So we convert into a discrete value transform, and then we take the DWT coefficients and applied thresholding over it. And normally what happens when you convert your signal into a DWT signals with the help of your mother wavelet. So mother wavelet is a kind of a signal which resembles same to your ECG signal. So your physiological signal. So you can take an example of ECG as a signal. So you can take any wavelet from a Dobbich's family, which resembles something similar to your ECG signal. It means it has some kind of pattern where you get one kind of, for example, PQRST is a kind of waveform pattern we have. So you can select a wavelet which will have something similar pattern, because noise is normally is random. So noise doesn't have any specific pattern such as. So normally noise signal you get is some kind of uh, even if as a pattern, but if you know what's the pattern of our physiological signal, with the help of some reference to it, we can denoise it. So, and after applying the threshold, we do inverse Fourier transform to again get back the original signal. So what we do is we take a signal. So in signal might have noise added with it. Then we do discrete Fourier transform and apply threshold to the DWT coefficients, where normally your noise signal has a very lesser amplitude, and once you apply the threshold, then subtract those components from your signal, and you do inverse wavelet transform. So as you already eliminated those noisy components from signal, and once you do inverse transform, so whatever you get is only the your required desired signal part of it. So, and physiological signals are being used on various variable devices nowadays. So your the heart rate, then SpO2 measurement, and EEG, blood pressure measurement, various parameters, and in many of them, like the machine learning and deep learning techniques are used to estimate the desired values. So what we can have from variable devices like a heart rate, then oxygen saturation, blood pressure, step count, ECG recording, we can have a arrhythmia detection, and exercise identification can be done with the help of your accelerometer and gyroscope sensors, and your sleep analysis that also can be done from your the movement. So what are the sensors available into it? So the sensors are your IMU sensor, PPG sensor, and ECG sensors. So in your so in your IMU sensor, which has accelerometer and gyroscope, you can perform activity classification, whether that person is walking, running, cycling, or maybe different kind of activity. PPG sensor used for the identification of your pulse rate, and ECG for the arrhythmia detection. So the IMU sensor, which has accelerometer, gyroscope, and magnetometer with it. So how it normally works is in this fashion. So depending on the different activity or different movement, the pattern of your the accelerometer and gyroscope signals varies. So in accelerometer, you can get data into three different axes, X, Y, and Z direction. Similarly, gyroscope data you can have in X, Y, Z direction. So you get, if you talk about accelerometer gyroscope, you'll get 6 signal components. And by doing pattern identification from those 6 components for the different activities, you can able to identify various activities performed with it. So again, the step counting can be done like acquire data, then we do signal processing is again everywhere. Then we do some kind of a smoothing to get peak to detect the peak from your signals, and you can by the peak detection you can identify the steps. This is how your step counting algorithm works in your, which normally can be found in almost all wearable devices nowadays. So this is your PPG sensor, and from your PPG sensor again you can identify or you can calculate the heart rate. So again, how it works, in most of the cases it goes into the same stages. You get a raw signal, then you do some kind of a pre-processing, that is a uh, noise removal, then you apply certain filters, so you get only a desired component to extract the required information. Like in case of a heart rate, you are just more just concerned about the peaks, so you don't bother about if you lose some kind of information out of it. So you'll just try to catch those peaks out of your signal, so you can apply some kind of smoothing, like a moving average is one kind of a smoothing filter which applies, so which helps you to identify the peaks from your signal, and you can then further calculate. Then again, your SpO2 measurement, you have two different LEDs where, so it works onto the Beard-Lambert slots. So you'll get the absorptivity changes for the different components. So for the oxygenated and deoxygenated hemoglobin, so you find an ratio of it and get in an your SpO2. So again, BP measurement with the PPG. So this is something, still it's not that accurate in almost all devices. You will get almost approximate value out of it. So I will talk about it later, how we can have raw PPG signal, and which kind of features we can extract, or which or what is the required information, how we can do some signal processing over the raw PPG to extract features. Those can be used for the estimation of blood pressure. So how it works is, in most of the wearable devices, you get change in the blood pressure, but you don't get actual value of it. So it's usually a two-step process where you have to calibrate it with the actual blood pressure value with the blood pressure device, like cup-based blood pressure device, where you can monitor your value. You can measure the value with conventional BP machines, and then provide that reference value in the device. So whenever there is a change in that reference value, as you already provided the reference value, and it can able to detect the change in your BP, so it can provide you both systolic and diastolic blood pressure values. So again, the ECG sensors. So Apple Watch is one example of it. So this is a ECG where uh, it works. There are two placement of ECG sensor. So one is on your wrist, so which is behind your watch, so which is connected to your wrist, and another is your uh, finger from your another hand. So let's say if watch is in a left hand, so you have to place any finger from your right hand onto that sensor, so that electrical connections will be complete, and you will get an your ECG signal. So this is how most of the ECG sensors into the wearable devices works. So yeah, so here you can say, you can even Apple Watch can give you idea about if there any kind of abnormality in your ECG or not. So you can go through the research done by the Apple team, and I have already provided a link in it. You can check out it later. So yeah, the CCG signal, you guys must be aware of it. So I am not going to explain each and every, but you should know like which are the different important component of your signal. That is a P wave, then you have a QRS complex, and in the T wave. So normally the ECG signal comprise of these components, and each and every component had its own significance. So identifying these components and extracting features out of this component will help you to identify if there any kind of abnormality present in it. So here you can say it's a P, then QRS, then a PR segment, ST. Again, there's a QT interval. So there are these are, you can say, features. So here I can say that PR interval is one of the feature uh, that I can use in my uh, machine learning model to do some kind of classification. Let's say I want to classify into various arrhythmia. So what I will provide, I will extract features. So from the raw ECG signal, I will identify the amplitude of P. Then I will take the PR interval. I will identify the amplitude of R, and these are my features. So all these values uh, I can consider as a feature. Apart from that, uh, what kind of other feature from time, frequency, and a wavelength domain that you can extract, and those extracted features, we do some kind of feature engineering later on. So in terms of ECG, so if I talk about time domain features, so time domain features are basically your intervals and amplitudes. And when we talk about your frequency domain features or your FFT coefficients or DCT coefficients, so these are my the frequency domain features. If I talk about wavelet domain features, then I will use some kind of again mother wavelet, maybe Dobbich's or Haar or Morlet or any other, and based on that I will take the discrete wavelet transform components. So once you transform your signal into a wavelet domain, you get two components out of it. One is the uh, one you get a detailed component, another is the approximation component. So out of your detail and approximation components, which will act as your features. So you can extract various features, and you check if there is some kind of a collinearity present within your features or not. Like two features might have same information with it. So if two features are very highly collinear, we take only one out of it. So this comes into the feature engineering part. So when we take an example of ECG arrhythmia detection, where we'll discuss it again, like how you can do feature engineering so that you can take only the key features from your uh, feature extraction process and train your model. So yeah, so ECG data, then we have from a QRS complex detection, we can the heart rate is and heart rate variability, the QRS complex detection is good enough. But if you want to go ahead and identify various arrhythmia as well, then you have to apply machine learning technique, machine learning or deep learning techniques. So when I talk machine learning and deep learning are machine learning. Deep learning is actually a part of machine learning, which is where we use artificial neural networks. But machine learning is a term we normally use when we have a small amount of data set and we are using conventional techniques over it. And when we talk about deep learning is where we have very large amount of data set and you do not have to do any kind of feature extraction. Model will itself uh, identify features from the available data set, and as you have in your artificial neural network, there are many layers in it, many layers. So your artificial neural network is very deep. So in that context, it is known as a deep learning. So deep learning is again a part of machine learning, but these terms are used uh, on the basis of how much data you have or whether you are doing feature extraction manually or not. So when you do feature extraction manually and have a limited amount of data, you go with the conventional machine learning techniques or model. And when you have lots of data with you and you're not sure which kind of features need to be extracted, in that case, your model architecture will identify features by themselves, and you can and model will learn from the data. So yeah, so we have discussed here QRS conflict detection and Pan-Tompkins algorithm. So this is a it's a example of a signal processing technique where you can use a raw ECG signal and can identify the peaks out of it. So where it happens is actually uh, 5 stages. So first you apply the band pass filter, then one sample difference, which is something similar to the applying derivative. So only your high frequency component will be highlighted. High frequency component in this case is your peak. So and then further smooth that signal with the moving sum, and you can identify the peak. We'll take an example of the same. Uh, yeah. So you guys have already have code with you. Hello.
Yes, sir. I have
Yes, sir.
shared. Sir.
Okay, you have shared the code with everyone, right?
Yes, sir.
Yes, sir.
Okay, fine. So we'll start working with Google Colab uh, so that you'll get used to the how you can use freely available tools to start performing on your data. So here, uh, if you have uploaded uh, this file, let's say, on your Google Drive, and if you open the IPython notebook, then Google will itself launch Google Colab for you. So
You
this
can
is a
give,
Google.
Kalpesh, you can give the steps actually. Otherwise, some of the students may be very new to this.
Yeah,
Uh,
sure. I'll just go through the steps so that as the session is already will be recorded, so that I can refer it later on.
yeah.
So yeah, so I think you already have the that particular folder, or alternatively you can uh, uh, using this GitHub link, you can clone this repository, or you can simply download the zip file from here and can upload it on your own Google Drive. And once you upload it on the Google Drive, if you click on this IPython notebook, this one, so as it will launch uh, this Google Colab for you. So in Google Colab, you can select the various runtimes. So runtime is like whether you want to use GPU, CPU, or TPU. TPU is a tensor processing unit from Google. So you have different options. If when you select none, so by default you will get only CPU, and when you select GPU, so you'll get an GPU. And even in GPU, you can select whether you want a standard GPU or a high RAM. So let's say if I select an high RAM GPU, it's useful when you want to train your model, because if you want to train your model, it requires lots of computational power, and you need a GPU for that purpose. So in your free account of Google Colab, you get it around 12 GB of GPU for 12 hours uninterrupted. So after 12 hours, it will automatically reset. So that in that case, you have to launch it again. In case of there is something called Google Colab Pro as well. So in Google Colab Pro, you get 24 hours uninterrupted GPU. So that if you have more data with you, and you know that your model will take more than 12 hours to train out of that particular data, you can go with the Google Colab Pro. These are very cheaper options. So this is not the standard way we train models in our company. We have cloud infrastructure for the same. So we use Amazon Web Services as well as Azure, uh, the Microsoft Azure cloud uh, to train our model. But as for students, I think Google Colab is the best way to begin with. Even Kaggle can provide you the free GPU service, but with from my experience, Google Colab since works well most of the time. It gives you around 12 hours of uninterrupted GPU. So let's say I selected this, and it will start allocating. So from here you will come to know that which GPU you have got access to. So in my case, I can say I have GPU RAM of around 52 GB, and the storage I have received is around yeah, 150 GB. So this will vary depending on account to account. So in my case, this. Okay, and in Google Colab, it is as good as your IPython notebook, where you can able to install different Python libraries. So if I want to install this MPL D3 library, I simply uh, put excellent this mark and pip then the install is a command in this particular library. So if I want to install wavelet library, which is wavelets, I can simply run it. So it's saying is already satisfied, so I already installed it. But in your case, it's not. You can by this command, you can install different libraries in it. Similarly, these are the import commands. So it's saying MPL D3 is not installed. So we install it. Okay, so it's ran successfully now because we have installed this library. Okay, the important step is mount your Google Drive with your Google Colab. Even though from your Google Drive itself, this Google Colab launch, but there is no linkage between them. So both are independent services. So as both are independent services, you need to connect your Google Drive with this Google Colab account. So this is a step for that. From google.colab import drive and then mount drive. So this is a standard command, same you can use in your as well. Then it will ask you for go to this link. You have to just simply select. You can sign in. Then you have to just copy this and paste it here. Enter. Once you enter this, you can able to view the files. Yeah. So now it is already linked with it. You can able to view your entire drive from here. So, you can view your drive, and again you have to cd to the directory is where my this particular project is available. So simply I can copy path and paste it here. So that will give me that path. So I need to connect it. So you'll get an idea like this is the location, which is my current directory now. So as this is my current directory, I can check which files are there. So these are two raw ECG signal files, and this is my the current notebook. So I can now simply load it. I'll just go through the demo first. So this is a raw ECG signal. That's what you have got. The pre-processed signal. And we'll apply Pan-Tompkins algorithm on this. So then it can able to identify the specs. So where we applied Pan-Tompkins algorithm here. As you already seen, the first step was to have a bandpass filter. So this is a bandpass filter. So from sp.signal, we have imported this Butterworth bandpass filter. So we have already imported those libraries here. So are you guys familiar with Python? Like, or it's not covered yet? Because anyone can answer. Hello.
Yes, sir, you're audible. Yes, sir,
Yeah. Uh, so uh, you are familiar with the Python programming or not yet?
yes, sir, some of the students are. We received one chat in the section saying ki yes, they are used to it. But if you could please give a general instruction so that everyone comes in one page.
Okay, sure. So in Python, you can do if you must have used maybe MATLAB in your academics. So whatever you can do with the MATLAB image processing, signal processing, same can be done with Python as well. So Python is an interpreter language. So you need not to bother about into the code syntaxes so much. So it's much simpler to use where uh, we'll import different Python packages, and you can provide, it's like providing a nickname to your library. So import NumPy as NP. So NumPy is a mathematical computation library. Then Pandas is again based on NumPy, where you can perform on your data, and you can perform various kind of columns and rows operations on your data. So SciPy is the scientific library where you have various kind of signal processing algorithm built in. So we import those existing libraries, or you can say Python package. You can simply find different Python packages if you want to install. You can quickly search on pip install, for example, pqtils. So from here you will get to know which is the current package available here. You will get project descriptions as well, and you can simply copy this, and you can run this here. So similarly, if I install any specific library, I'll just simply request. So it will download and then it will install. So you can install, once you install those libraries, you can simply import it here. So if someone wants to uh, download some specific version of it, maybe 1.3.3, you're not comfortable with it, you want older version of it, you can uh, go to the release history and can download specific version. So yeah, so that's 1.3.0 version now you can download. So you can download online as well as you can download offline. So this is the way you can install the packages. This is the way you can import the libraries. And if you're working on Google Colab, this is a very important step, that you have to mount your drive so that you can get access to your codes and the data set that you have uploaded. What I usually do is I use Google Drive desktop application. So in Google Drive desktop application, I can uh, sync that specific folder. So I've already synced this folder with my Google Drive account. So if I do any changes locally, that will automatically will be reflected into my drive. So I need not to download again. And this is the way even you guys can follow. So you can use this Google Drive application, desktop application, and you can sync any specific folder as well with your Google Drive, so that whatever changes you do, or let's say I want to add another data into it, so and the data is available in my local system, so I simply copy paste that data into that local directory, my local folder. As it is synced with my Google Drive, it will automatically will be synced, so that you can able to access here directly. Yeah, so yeah, this is bandpass filter. Again, it is available into the SciPy library. You can go to that pip install SciPy and you'll get that documentation of it. So what are the different options available it, what are the different filters available with it. Then there's a function for moving some, and this is for the pig detection. For the pig detection, you can play with as a part of assignment. After this, you can play with different pig detection algorithm in the same workbook. So instead of this find pig technique, you can use pig detection with continuous wavelet transform, or pig detection with the pig utils kind of thing, or you can create your own uh, uh, pure pig detection algorithm. So this is how we can play with Google Colab. So we'll move ahead, and then we can see for machine learning uh, models how we can use Google Colab to train our data, and then further. So you guys can try out later. Uh, I think is already available with you. Upload on Google Drive and play with it. So this is how I've already explained the difference between machine learning and deep learning. So in terms of medical imaging, like the feature extraction, feature selection, and it will be done by us manually. But in terms of deep learning, that has been taken care by your model architecture itself. So we'll see different medical imaging applications where you can use different models or different computer vision techniques to extract different informations. These are the I provided a link of some of the free data sets that you can take advantage. Kaggle is the famous one where you get almost uh, different kind of data sets available, including medical data set. Physionet is one of another popular website. Even Google has their own data set search. So in that you can search the required library. For example, you go on X-ray images. So you can search for X-ray images, and then you can that will lead to different sources, free as well as paid sources, and you can select uh, desired one. So you can look into this later on. So the computer vision, there are what you can say four major categories. So when you get an image and you just want to classify whether that particular image is of which category. So for example, if you have X-ray image and just want to know whether that image is of that particular person has a pneumonia or not. You are not bothered about location of your pneumonia, but just concerned about whether pneumonia is there or not. So simply you want to classify image. Uh, the simplest example is uh, dog versus cat classification, where we have some of the images of the dog and some of the images of the cat, and you just want to classify whether that image is of a dog or cat. That comes into the image classification. Second is object detection, where in your image there are multiple objects. So this is example where there are five people standing in one image, and your object detection is a technique where you can able to identify all the different objects present within your single image. So it can locate the position of your object as well and can identify individual objects. But in case of semantic segmentation, you want exact boundary of that particular object, then you go with the semantic segmentation. But semantic segmentation, here is a catch. If there is an overlap between the two objects, so that overlap will be considered as a single object. So as you can see here, the these five people are very close to each other. There is some sort of overlap. So it able to detect the boundary, but whenever there is overlap, it detects it as a single person. So there are some applications where you are interested in semantic segmentation, where you don't bother about the overlap, and there are applications you work on instance segmentation where you want every object to be distinctly identified. So here the example of the instance segmentation, where you can able to detect 10 different objects and identify along with the boundaries, you can identify their relative positions. It identifies each and every person's differently. So these are the terms when you uh, uh, search about medical imaging or maybe search about computer vision in general. These are the basic terminologies you should be aware of. That is image. When I say image classification, I'm not bothered about the position of that particular object in the image. I'm just concerned about whether that particular object is present or not. When I say object detection, I am concerned about uh, the position of that particular object as well. And in that case, there are possibility of having multiple objects in a single image. So there may be possible where you have a person as well as you can have different animals in the same image. That again comes into the object detection. Uh, so we'll take each and this example with context to the medical imaging. So you have image classification where you want to classify whether that image is a normal or having a bacterial pneumonia or a viral pneumonia. So here when you do annotation for these such images, annotation means labeling, because your model won't learn by itself. You have to provide it some kind of a reference data. So what you will say that this is a normal image. So what we usually do in image classification is we create different folders. So I will create an folder for a normal, create a folder for a bacterial pneumonia, and create a folder for a viral pneumonia, and we'll save subsequent images into those folders. So your model will automatically load images from those folders and can learn by themselves. When you talk about object detection, this is an example of the object detection where in object detection you can able to identify the overlap objects as well, but you don't get exact boundary of it. So even though your cell is somewhat uh, circular or elliptical shape, it will draw the square box or sorry bounding box around it, and bounding box, so you will get to know that your object is within this bounding box, but you won't getting any exact dimensions of that particular object. So when your task is to identify uh, different elements and count it, and you are not bothered about their exact dimensions, then you can go with the object detection. Dimensions, I mean, you're not bothered about the area or a volume of it. So in that case, you will go with object detection because object detection is a faster than your semantic segmentation or your instance segmentation. So in case of object detection, the annotation method varies. So here, first you have to manually annotate each and every cell. You have to draw the bounding box around the cell and label it that this particular bounding box is RBC and this particular is platelet, this particular is a WBC. So when we talk about annotation, there are different annotation tools available for us. Many of them are free. CVAT is one of the tool. Then Label IMG is one of the tool. There are so many. VIA VGG annotator is another tool. So what this tool will give you is it can load multiple images at a time in your as a part of your project, and you can take one image, can draw the boundary around it, and can name these images with subsequent labels, and you can save into a one specific kind of format. So there are different format, like for the object detection, the common formats are COCOA format, and another is Pascal VOC format. There's another object detection technique which is called a YOLO. So, and YOLO is a one-stage object detector where it has its own format till YOLO V5. There are different versions of YOLO. Maybe in next session we'll take an example of object detection on images. So then we'll talk about different object detection algorithm, how you can annotate your data, how you can load that annotated data and can train it, and then how you can even after annotation there are different standard formats. So you have to convert in one format to into another based on which object detection model you will be working on. So this is example of object detection, and this is example of semantic segmentation where you want to detect the tumor. So where you are not as there is no kind of overlap, you are not concerned about the presence of overlapping objects, and you just concerned about the continuous segment. In that case, you can go ahead with the semantic segmentation. And this is an example of instance segmentation. So here you can say in semantic segmentation, whenever there are the two overlap objects, those those objects won't be distinctly classified. But in case of instance segmentation, you can basically classify whether that particular is of uh, even in that same you can find variation in it. So here you can observe with the semantic segmentation, this whatever part was an overlap part, that either that can be into a single uh, one single cell, or you can you can basically clip out certain section of it. So in any of the case, if you go with the semantic segmentation, you will lose actual information. So actual information is like this uh, particular cell is dimensions are like this, but as you wanted to avoid the overlapping, you have clipped it, so you actually lose some information here. So based on your requirement, you can uh, customize and can use different image processing techniques. So again, this is an example of pathological image. In pathology, what happens is, for example, I want to identify uh, presence of cervical cancer. So in identification of the cervical uh, cancer, we uh, take pap smear images. So in pap smear images, what we do is under the automated microscope, we capture the images with the higher magnification. It's around 100x magnification, and those images are stitched together to form this single big high resolution image. But now you want to identify any kind of abnormality within it. So to identify any kind of abnormality within this high resolution as a very single stitch image, you can't do it directly. You have to convert it into a patches. So patches is something which is of a fixed field of view. Field of view is this is the one image or one frame from this big resolution image, which is zooming into, let's say, 100x magnification. After zooming into 100x magnification, you get this image. So what your annotator, in this case annotator will be expert pathologist. So what expert pathologists will do, they will basically label the any if any abnormalities into it, and those labeled images will be further given to your convolution neural network to learn out of it. So again, in real use case, as your original image will be very high resolution single stitch image, uh, to train your model, you have to patch first, and you have to do annotation on patched images, and then give to the training. And on actual image, when you do inference, or inference is term for the prediction from your raw image, again you have to convert into your patches and apply your model on that particular patch, and again you have to provide uh, prediction on that particular patch. So uh, that happens in automated fashion. So you need not to manually crop it and provide to the model. You can write down a code where it can take one particular patch or one particular field of view, which is of 100x magnification, and can uh, load you can load your trained model on it and can do inference over it. So yeah, so CNN for the image classification, how it works. Normally, you get an input image, and it has uh, convolution filters, and along with uh, different activation functions. So, what is yeah? So as we already seen that we don't extract features manually in deep learning. So CNN is a deep learning technique. There's a convolution neural network. So it is known as a convolution neural networks because we use convolution filters, various convolution filters here. So and those convolution filters are followed by activation functions. Activation functions are actually non-linear functions which can extract the best out of the non-linearity within your signal. So the ReLU, which is the rectify linear unit, is one of the activation functions. So there are other activation functions like a sigmoid and all. So each and every activation functions has its own significance. So when we take an example of object detection, and I think maybe next session where we'll take images of peripheral blood smear and identify the various cells out of it. In there at that time we can deep dive more into it. So I just wanted to give you a rough idea that uh, uh, once you take a raw image and you apply the convolution layer, so you get some kind of a feature map. So based on which kernel you use, you'll get different feature maps, and those feature maps you provide to a pooling layer. So pooling layer basically uh, converts the high spatial resolution images into a low resolution one. So what happens in initial stage of CNN, you extract very simple features. Very simple features is like this. So you extract uh, only maybe edges, or you can extract some kind of boundaries only in your initial layers. When you go into a deeper layer, you start identifying different patterns. So in initial layer, you identify only boundaries, let's say, or edges, and in subsequent layer, you start identifying pattern. And when you go more deeper into the network, you start identifying various shapes. So this is after applying so many layers, you'll get this. This is how CNN works. You can do deep dive into it further. So what I can do is I can take one particular field of view. Uh, so this is my image, and in that particular image, my filter applies on one particular section, and that one and it extract features from that particular section. Similarly, this filter will apply all over this particular image, and it will generate different feature maps. And based on those feature maps, it will let's say if I use a Sobel filter uh, as my convolution mask. So in that case, what Sobel will do will give me an edge. So based on which kind of a filter I will use, I will get different kind of features out it. But this happens in automated fashion. So it applies various filters and extract different features by own, and based on your loss function. So loss function is something which compares your model prediction with your ground truth. So uh, what I mean by ground truth is that let's say I have this particular image, and I know that abnormality present in one particular section, let's say this section of the image. And what I will do, my model will learn and try to identify that region where abnormality is there. And let's see if I identify abnormality somewhere here. So whatever the loss, that will be very high. So from the loss function, your model will come to know that it has learned something out of it or not. As it's not learned, so subsequent weightages are changed to those filters. So uh, based on that, it automatically identify various combinations of various filters. And let's say in ideal scenario, if actual ground truth, where which gives you a reference to the position of your abnormality, and your model predicts the same, in that case loss will be very low. So loss function is basically kind of error function, so which gives you an idea about whether your model has been learned or not, so that whether you want to stop learning or you want to continue learning, so that you can uh, come to know from the loss function. So uh, till now I've given you very high overview of CNN. So what we have learned is there are different components present in CNN. One is a convolution, then pooling, then fully connected. There's a networks like a region proposal network and skip connections, identity blocks. And all. So this is how convolution works. So it takes, let's say there's some input data. This is a kernel, maybe any kind of filter here. Then it applies on this my input data. There's a convolution operation, and you'll get convoluted features. So it calculates features with this with varying kernels. So happens this way in automated fashion. So these kernels are applied to various positions, and these feature maps are generated. So the feature extraction process is happening automatically, and various combinations of kernels are used in automated fashion, and it will check whether whatever information, based on whatever information, what the prediction is matching with your reference label or not. If it is not matching, then it will provide those negative weights, and on based on that, it will model will come to know that whatever filter you use, it's not learning anything. So it will try to change that combination and can learn. So yeah, so after applying a convolution, we apply something called ReLU, as a rectified linear unit. So you will get an like idea of what you will get after the rectified image. So uh, it eliminates all the black components of your image on and only take the gray and white. You will get only white components. So as you have seen, this is a function of ReLU. I'm explaining ReLU because if you start working on any medical imaging project with the convolution neural network, there's a very you will definitely come across with this, the ReLU activation functions. So how it works and what's the significance of the ReLU, to getting an idea about it is important. That's why I've included here. So this is how you apply the input, you apply convolution layer, and then you apply ReLU. So after output feature detector, you'll get something like that. And after applying a rectified linear, you get this particular kind of information. So then after that, we apply pooling layer. Uh, Pooling layer are used to reduce the dimension of the feature maps, and basically it helps you to reduce a number of parameters. Uh, to train your model. So and what it gives you is only the important part of your image. So whatever the redundant part of the image will get automatically eliminated. So there are different techniques for that. It's okay if you don't understand much about it, but just uh, remember these are the important steps while you do CNN. So even if you can't get it right now, but just note it down so that you can deep dive into it later. So this is how the uh, what only the important or high frequency information has been captured from your this image with the help of transform. So uh, it helps you for your as if your image is very high resolution. So and even after applying filters, you will still get very feature maps of a uh, very high dimension. So as your model, as you have very high resolution data with you, and as you train your model, the computational power requirement becomes more and more. So if you have limited computational power and inference times is also becomes critical, so you want your model to be operate in a very fast uh, format without compromising with the accuracy much. So in that case, the max pooling layer comes handy with you. So it's basically a combination of convolution layer. Then you applied convolution and pooling happens one after another. So convolution followed by normally ReLU and then the pooling layer. Then the step goes on. So in initial stage, as we've seen, you get very basic features, and as spatial resolution is uh, decreasing with each and every layer, you get more high level features. So you start recognizing shapes and in subsequent layers of it. So yeah, once you apply convolution layer and the uh, pooling layer, then you apply the fully connected layer. So fully connected layer is actually uh, your conventional ANN where each and every uh, neuron is connected with another neuron of subsequent layer. So uh, whatever all the possible combination of information can be extracted is extracted in the final layer normally. So this is a conventional CNN model architecture where you get an input image, and from that particular input image you apply various convolution filters. After convolution filters you uh, apply pooling layer. It gives you two advantages. It reduces your spatial resolution as well as it reduces number of parameters your model need to learn, so that whatever the processing time will be reduced. Also you can extract more high level features out of your when I say low level features are your edges or lines, boundaries and all, and high level features is like actual patterns or maybe a texture. These are high level features. So yeah, and then further uh, uh, this is the role of fully connected layer so that we can get maximum uh, out of uh, whatever features has been extracted by your convolution layers. And then further you can apply to a softmax activation function, which can help you to generate probability for each class. So this is how we have seen previously, right? So this is the architecture of image classification. So this is your image, uh, this original image of this particular flower, and sliding window is applied. On the sliding window, uh, your different convolution filters are applied that will generate different that will generate a feature map Then you applied max pooling so that you will get more complex shape. So as your spatial resolution is decreased, and you can further extract more complex shapes. And once you get all information, then that information is passed to the FC layer, that is fully convolution layer, to get to extract maximum information out of it. And then further you apply something called softmax layer, so which is actually your classifier. So based on your feature maps, it can provide the class probabilities. So these are the basic components you can find in any image classification model. So this is how softmax works. Again, you can have it will give you the probabilities of different classes based on the feature map. So this is how, if this is the feature map I have passed, then softnet function is based on that feature maps, gives and find and probability of each class. Apart from the image classification, another important model is a unit architecture. So as we seen here, there is something called FC layer, right? Fully convolution layer was there, but this FC layer is computationally expensive, and to eliminate that, there is something, another technique is introduced in the model, that is unit, which was initially developed for medical image segmentation. But this technique is so state of the art that many components of this model architecture are utilized in the different model as well. So this is the architecture of UNet, where you apply the input image. So now you'll get to know, like, again in UNet there are again convolution layer, then max pooling layer, then again convolution layer. So convolution, max pooling, these are very uh, common units in your convolution unit models. So knowing what is the significance of each and every component will help you to understand any model architecture. So it's a architecture where you have encoder followed by a decoder. So what encoder is doing? Encoder gives you an idea about what is present in your image. So when I say what is present in image, it basically identify various features, and based on those features, uh, it will identify presence of any particular class within it. But to locate where exactly that particular object is present within that image, unit has an additional level. So uh, from this input to this particular part, it is same as that of your conventional CNN. Uh, and after that, there's another unit which is the decoder. So as we say, with subsequent layer, the spatial resolution of the image is decreasing. So whatever you get to know, the high resolution image is actually is like getting degraded. So you get to know what present in that particular image, but you in order to do that, you lose spatial information. So if I talk about spatial information, is like information of the location, because you already degraded your original image such that you in context to your original image, where exactly the position of that particular image, you can't get it back. So in order to achieve that, in unit has a decoder unit. So uh, uh, instead of max pooling, there is a something different techniques is used. So uh, uh, so here we'll do up convolution. So up convolution will convert your it will increase the resolution of your image by passing the information from the previous layer. So you can say there are these lines. So what it is, so with every convolution operation, the image spatial resolution gets decreasing. So your positional information is, we start losing positional information when we apply convolution filters. So to get back the previous positional information, UNIT introduces something called skip connection. So this is a skip connection where you can pass the information from one layer to any layer. So this is again later introduced into the another architecture, that is Resonate. But even before the Resonate, Unit has provided this feature where you can pass out information from one layer to another layer, so that that layer will get an help to regenerate the positional information. So this is how uh, uh, this is how up convolution works. So up convolution is basically I'll be converting my uh, the after applying the mask over my one particular cell component. Instead of one, there will be four components will be generated. So it's a from a lower spatial resolution, we are converting to a higher spatial resolution. That has been achieved by something called transpose convolution. So in transpose convolution, so here is a input is of 2 by 2, matrix is of 2 by 2, and from the 2 by 2 matrix we can get output of 3 by 3. So as you know, so 2 by the resolution is now increased. So this is known called as the upsampling. So in downsampling, we have with max pooling, we decrease the matrix size. But with upsampling, which is the transpose convolution, we start increasing the size, so that will I get to know the positional information, or where that object is present in relative to that particular image. So again, the Resonate is another architecture where you have a combination of convolution, max pooling, uh, and along with that, there's a skip connection. So in UNIT, connections from one layer to another were in a fixed format. So the connection were freeze in such a way that uh, at the first layer where uh, your first encoder layer will provided information to the subsequent decoder layer into one particular uh, fixed level only. But in case of skip connection with resonate, you can literally can pass one particular output of one particular layer to any other layer. So here output from this layer was passed directly to this layer. Again, this layer to directly passes to this layer. So it was fixed. The pattern was fixed. But in case of this resonant architecture, you can actually pass information from one layer to another layer. I think now till now you might have understood why I need to pass information from one layer to another layer, because when I apply more and more layer to my model, I will start losing spatial resolution or low level information from my image. And to get back some sort of low, after applying so many filters, you will come to a stage where you wanted to extract further features, but your image is degraded in such a way that you can't extract further features at all. So in such a case, you provide back reference of or back any output from any layer to any other layer. So in combination, feature extraction can be possible. So in such a way, your CNN architecture can internally identify various possibilities, or you can say various feature maps, and it will select best possible combination based on the output provided by your loss function. So yeah, this is the same thing. It helps to train really deep network from very start, uh, so that you want, even after your spatial information is lost from one layer to another, you can get back. Uh, there is another state-of-the-art model that is a faster RCNN. So the faster RCNN, along with your convolutions and the pooling layer, there is something called Resin proposal networks. So that actually estimates the uh, possible position of your object within that image. So the feature maps are generated, and in addition to the feature maps, it generates anchor boxes. So the anchor boxes will give you the relative positions uh, of that particular object within an image. So this was introduced first into the faster Asinian model. So this is another example. So faster Asinian model is used for object detection, and as in object detection, we want relative or you can say position of that particular object within an image. So we need to generate anchor boxes, which is something called of bounding boxes. So we have to identify a position of that object. In that case, we use faster RCNN. So if in your case, if you want uh, only to identify whether, let's say, pneumonia is there or not in that particular image, in that case, it will be an example of image classification. So you can go with the conventional CNN model where you can apply convolution pooling that way, and apply a fully connected layer and provide a soft mix, uh, and can classify image. But if your task is to identify the position of that particular object or abnormality within that particular image, you can use architecture like faster RCNN. So based on your project or based on your task, you can take a call which model you can use as a baseline model. So what I mean by baseline model is a model which you begin with uh, as a possible solution to your problem, and you try to use that model and then do custom modifications in that particular model to achieve the desired result. So selection of your baseline model depends on the task you have. So in case of RBC WBC plexus detection, or detection of presence of pneumonia, uh, uh, identify the location of the pneumonia is an example of object detection where you can get you take advantage of this kind of model. Another is a mask CNN model, which is the next addition into the faster RCNN. Along with the faster RCNN, there is something called a mask head is applied. So that mask head will give you an idea about uh, presence of in presence of multiple instances of same object. So here object is only a person. So if there are in case of object detection, it can only identify there are four persons, and it and if there was any kind of overlap, it won't able to if you want any kind of boundary from that particular object, you won't able to detect it. So masquerade is something from your bounding box detection, you get actual boundary of that particular object, or you can say actual shape of that particular object. In case of object detection, you get only the bounding box, that is a rectangular kind of box you will get, but you don't know actual shape of that particular object. But if you want actual shape of that particular object, you can use masker skin as your base model. So which will give, along with the bounding boxes, it will give you the actual shape of that particular object. Apart from that, you can take advantage of transfer learning. For example, that's you decided that you want to go with object detection technique to identify RBC, WBC, and platelets present in your image, and you have only 1,000 such images. And as you know that your deep learning model won't work on the less amount of data. It needs lots of data in the more than 10,000 or more in lakhs actually. So transfer learning is a technique by which uh, whatever learned from another model, that information you can use it and can add additional layer on top of that particular model. For example, ImageNet in ImageNet challenge Inception is a famous model. In 2002, from that ImageNet channel, due to the Inception, you can say deep learning become very popular, and nowadays uh, lots of attention was given to the different research activities happening in this field. Most of the big credit can be given to the Inception model. That model was trained on very large set of data, different objects, persons, and the animals, whatever you can search from in Google, and based on that, that model was developed. So, as you're already aware that your convolution neural network model learns in each and every layer, in subsequent layer, it extracts different information. So even if your object, in your case, object is RBC, WBC, or platelet, but age detection is age detection, right? So CNN model, which is trained on lakhs of data, can obviously detect ages better than the model which is trained on 1,000 number of images. So that's the idea of transfer learning. So what you do, you know that in initial layer of your model can is the task of detecting very simple features. So you only put those layers. So those layers, I mean to say, the weight values of those specific layers are adopted into your model, and when you know that after that particular layer your model start identifying high level features or your problem specific features. So on those after those particular layers you can apply your own. So this is how transfer learning is being leveraged. So in most of the cases, the specific features or problem specific features are extracted in your FC layer. FC layer is known as a fully connected layer. So in fully connected layer, you normally, as you extract many features, and based on those feature map, the problem specific features are extracted in your fully connected layer. So what we normally do in the transfer learning is that I will use pre-trained weights of any other model. So I can use pre-trained weight of ResNet 101 model, or I can use a pre-trained weights of Inception V2 or V3 model, and can train only the FC layer, fully connection layer. So what advantage it gives me that even though I have only a limited set of data, uh, whatever possible weight values which are can be used to extract low level information will be used uh, with reference to the model train on a very high data, and whatever your problem specific information extraction part is there, that can be further uh, done independently. So this is the way. Again, in some cases, you only FC layer is not sufficient. You can skip some of the convolution layers as well, and you can say your model that from that inception model only only load weights up to, let's say, 14 layers. So you know that after 14 layers, your model start expecting your problem specific information. So you can train only that. You can you use those pre-trained model weights, and only so that those weights will be freeze, though those weights won't be changed. Only the weights of your problem specific layers will be changed. So yeah, this is how transfer learning works, and this is very handy because in your case as well, you have to go for a transfer learning, because if you're going to collect your data from your own, in that case you won't be able to get data in lakhs maybe, or even if you get data in lakhs, you won't able to annotate that data, because annotation is not always job of a layman. You need to have some kind of expertise based on the domain requirement. For example, if you want to annotate a model for annotate the image data for cervical cancer, so in that case, that the person who is annotating should aware that which kind of abnormalities, squamous cells may be present, that you can classify as a type of cervical cancer or not. So because of this reason, I guess you can always be using transfer learning. Then you can use yeah, so, there's a different this I think we can discuss later on. This is what something I talk about loss functions. So loss functions is there are different loss functions based on your uh, kind of data you have, kind of model you have. So uh, in case you have very imbalanced kind of data set. So if I talk about imbalanced kind of data set, for example, digital pathology data, you normally find lymphocyte neutrophils in a very high number, but in compared to that, the basophils are very few. So obviously, in your data set, whatever data set you will get, in that count of basophils will be very less, and there is a very high probability that your model won't able to identify it. So in such a case, you can use different loss functions which can highlight or which can provide higher weightage to your imbalance classes. So these are that's the reason loss function is also very equally important part of it. The focal loss is one of the loss function which is normally used in imbalance classes. Apart from that, you can uh, uh, along with this high level terminology, there is again something called optimizers, which actually helps you to derive the weights. So the weights and your weights will be updated with the help of gradient descent. This is one of the optimizer. There are different optimizers. Adam is another example of it. So maybe in the where we actually take a look into object detection technique, uh, we can further. So apart from this, another important aspect is model interpretation. So if you uh, identify one particular abnormality, then if you can explain it, like what's the reason your model is predicted that particular tumor or that particular abnormality. So there are certain for that. So model explainability is something very important in healthcare, because if you given a wrong call and there is not enough confidence in it, so based on that, uh, doing a treatment will be very risky thing. So if you provide explainability to of your model, like your model generated this particular result and these are the reasons for the same. So there are different techniques for that. GradCam is one of the technique, which if I identify that this particular object belongs to uh, whether in this particular image whether WBC is present or not. So GradCam will say that your model has highlighted this particular section compared to other sections. It can generate a heat map kind of thing. So that uh, gives you an more confidence in your model that yeah, whatever model is giving predicting a result is actually is making some sense. Like it's not doing it randomly. So there is technique by which you can apply GradCam. So maybe I'll share some of the code with you where you can try out by yourself. Randy, uh, for I would like to take questions if you have any. So the idea was to give an high level information to you so that if you go ahead with any project, let's say with the physiological signals, so in what you can do with those kind of physiological signals, how signal processing is important, what are the different signal processing techniques availability, what kind of parameters can be estimated, uh, so those kind of thing. And again, medical imaging is entirely different ball game where you there are so many different uh, techniques that you have to follow based on what kind of a task you have. So what are the most frequent component that you will came across? I'll try to cover into it. But if you have any doubts, feel free to ask me. Yeah.
Sir, if you could just open up your chat box, the questions are already there.
Okay.
If anyone can just read out the questions, it will be easy.
Yes, yes, ma'am. So,
Yeah. One question is, yeah, I'll go through it.
okay, sir.
Deep learning on a signal data. So if you want to do deep learning on a signal data, first you have to convert your signal data into CNN compatible format. So you have to convert into 1 cross 1, uh, where as transfer learning, you're aware of that, where you take advantage of already trained models. So if uh, there is a one particular model which is already trained on the ECG kind of a data, so CNN model which is trained on the ECG kind of data, or in that case you may able to use it. But if it is used, uh, but if you want to use ECG or a signal, physiological signal kind of data, which is actually kind of time series data. So you have amplitude variations. So you convert that amplitude variation into a image kind of format. So there is a conversion technique for the same. So you convert that into a one-dimensional and then feed it to your CNN model. In that case, you may not able to use pre-trained weights. So another is, which one is more computationally heavy, object detection? Yeah, instance segmentation will be computationally heavy, because in instance segmentation, what you are doing, it's a object detection plus mask detection, something like that. So you are in instance segmentation, you get bounding boxes as well as you get the boundary of that particular object. So in that you have to the mask generation is an additional step that is used. Again, it varies based on which kind of object detector you use. So YOLO, which is an single shot kind of detector where you do localization and classification in one step. Or if you can go with the where it two stages detector like a faster CNN. So even in object detection, the speed varies based on which kind of model architecture you use. How many number of kernels will be required? Okay. So yeah, what we do is first question is how many number of layers you need. You know? So because you can't keep adding convolution max pooling endlessly. So what we do is we keep adding layers till model starts overfitting it. So if you what do you mean by overfitting is uh, your model won't able to generalize that well. So uh, uh, so basically your model will be uh, learning on what kind of a data set you have provided uh, to it. But if you provide some different variations into a data set, it won't able to identify it. So that can be identified from your validation and training loss. So if your training loss is very low and your validation loss is higher, so you will come to know that your model is started overfitting. So you keep increasing layers uh, and you stop normally when your validation loss is much higher compared to your like uh, training loss. Can we use unit for object? Unit is used for semantic segmentation. In unit, uh, you must have observed that in unit, you don't have any kind of fully convolution layer. It is completely uh, what you can say fully convolutional layer. So fully connected layer is not present. So instead of fully connected layer, there is a we get use of one cross one filter. So with the one cross one filter, with the help of one cross one filter, the boundary mappings is being extracted. So for the boundary extraction, the one cross one filter is used in the unit. Uh, so uh, you if you only want to go for encoder part of your unit, you might able to use it, but it's completely different architecture. If you want to use unit for object detection, obviously we can do that. But why will do that? Like for the uh, uh, for if you want semantic segmentation, in that case you will go for a unit. In object detection you will use subsequent architecture. But if it's possible, then it's possible, you can do. Okay. The last question is very interesting one. There is something called knowledge distillation technique. So what this knowledge distillation technique is, let's say I wanted to deploy object detection model on mobile device, right? So your mobile device is computationally low device compared to what you get on your cloud. In cloud, you have privilege to use high computational GPU and all, but in mobile devices, again, mobile device computational power varies depending on the mobile to mobile, whether which kind of GPU and which kind of processor is within it. So what we do is we train model with the very what you can say complex architectures like ResNet. Let's say I train model with the ResNet 101. I will train ResNet with the 101. Uh, Again, I will do transfer learning with the ResNet 101, and I will save my logits value. Logits values are like output values of your fully connection layers that I will save. I can have another model in ensemble with that model. So along with the ResNet 101, I can go with the Inception v2. So again, I will use Inception v2 and save logits value of it and take average of those logits values and use those logits values with the ME loss. So that is your mean error loss uh, you can use with your low computationally low model like a MobileNet V2 or a MobileNet V3. So whatever information you have gathered from the high level model can be used, or that knowledge can be transferred into the your low level model to compute the loss. So mean square error loss is calculated, but your prediction will happen only on your computationally low model. So yeah, that's possible, and this is known as a knowledge distillation technique, where you can take advantage of high level model logics values to calculate the loss on your uh, low model, maybe YOLO or MobileNet V2 or something like that. Yeah, apart from that, you can play with the different activation functions as well. So different activation functions, and you can specify different kernels as well. So it again depends on whether your model started overfitting or not. So you keep changing it, and from your training and validation loss, you'll come to know that what is good for your model. So if your training loss and validation loss is not improving at all, so you know that your model is underfit. So if your model is underfit, so whatever parameters you have tuned into your model are not working for you. So you need to tune your model, or maybe whatever data you have provided, that is not sufficient at all. So maybe you have to do data augmentation, where you provide synthetic kind of a data. Maybe you play with a different filters. You can play with the different activation functions. You can play with different learning rates. You can play with different generalization techniques, like applying a dropout and all. So based on how much your validation and training loss, you normally take a call, like whether you wanted to tweak those parameters or not. And again, you can play with optimizers as well. So stochastic gradient descent or ADAM are some of the optimizers, and you can say whether which optimizer is helping to converge your model. Yeah. So yeah, so it won't increase the size of low level model, because you are only use the weights from that particular model to compute the loss. So its idea is like you're using combination of or ensemble of a high level model and your low level model for a training, but for a prediction you are using only a low level model. So knowledge distillation actually will help you in that case. I think I have answered most of the questions. Any other questions?
Thank you so much, sir, for answering all the doubts. I would like to call Rutuja to share some instructions. Over to you, Rutuja.
Yes, hello guys. The link for the feedback form and the assignment questions will be shared soon. So you are requested to complete the assignment before 7th of September. That is the next session of the SIR. And you have 2 to 3 days for exploring the all the things, and we hope so you complete the assignment till 7th of September. Over to you, Kashvi.
Okay, so I hope you will practice with the Google Colab. I have provided the repo as well, so you can upload it and work on your Google Colab notebook. You can go through it, some of the basics of CNN again, object detection, instance segmentation, and all, and so that once we'll take an actual example of the object detection, so uh, we can go more deep dive into it, but you can ask more questions if you uh, I think you read about it. So just go through it. Some assignments I have given where like questions which will help you to understand our next session. So that will be more hands-on, where we'll be working on some of the image data set for object detection kind of problem. and we'll discuss object detection maybe on more detail in that case. Yeah, I think I'm done with it. So
Thank you, sir. Today, my words are not enough to express my gratitude towards you. Thank you so much for taking out your precious time in conducting this session, giving us such great insights on AI healthcare applications, specifically about various recent innovations in wearable devices, also different types of signals and signal processing techniques. I'm sure every participant now has a very good idea about signal processing, computer vision techniques, deep learning techniques, and much more. I would request Geeta Narayanan ma'am to share a few words of today's experience. Over to you, ma'am.
Hello, Kalpesh. Actually, the session was very nice, and hope students could understand. And I would like to say here that if the artificial intelligence and the deep learning need to be explained, some background about Python is required, but Kalpesh has tried to explain everything without even the Python. He has explained many algorithms, and it is a high level topic as such, artificial intelligence. Those who are really interested, they take up projects on that. So he tried to explain many new fields also in that, like CNN and all, and basic algorithms also he has explained. So it was a nice session. Maybe some of the students who are not familiar with the artificial intelligence and the terms which are there, they might have found it little difficult. But then I feel if you are doing this assignment sincerely, you try to find out. Only the questions are given. In the question, you can just find out what is it. You Google and find out. Then also you will understand the next session in a very nice way, and also go through the folder which is shared with you. And about Kalpesh, I remember him as a student also. When I joined Vidyalangar in 2007, I think 2008 he was in second year, or 2007 he was in second year. And if I remember correctly, I was his mentor for training also. There was a training which used to be there in the final year. Those times, 7 semester was only industrial training. There was no teaching, no subject to be learned. That time, if I remember correctly, I was his mentor, and I remember visiting his company also. He was doing in a company. He was very inquisitive student since when he was a student itself. So all the very best to Kalpesh. Thank you for accepting our invitation and coming here. Thank you, Kalpesh.
yeah, sure. Yes, I just wanted to say to all students that you should do whatever that fills you, that you are interested in it. So I have taken a very unusual path towards, if you talk about my career. So I did my B in biomedical engineering, but I worked into the electronics and embedded after it because I was more interested towards embedded system like programming microcontrollers, and also because of my final project that was a prosthetic arm, I was more interested into it. And after working into electronics and embedded, I got interested into the artificial intelligence, machine learning, and deep learning. Again, that was my master's project, which was based on radial arterial pulse, that is Nadi Pariksha in another term, you can say. So, uh, so then I had some offers in another companies, like, but I wanted to uh, work into the field of AI only, so that's why I opted to work in a startup and taken a job as a data scientist there, and working into a fitness and healthcare field for around 6 years. Currently, actually, I'm working into automotive domain. So the work is towards more autonomous driving, driver assisting, related to that. But still, it's what I currently am interested in it. So where autonomous, there's a domain where lots of things are happening, where AI on edge deployment is happening, and that is something of my interest. I think one student has already asked some questions related to that, but AI on edge is something is very evolving, and healthcare and automotive domain are the two domain where it is being lots of research and lots of interesting things are happening. So that's why I changed that. So uh, I took a risk, and based on my interest, and it proven to be good so far. So you students can also follow your passions, whatever interested to you. You can obviously you can take help of amazing mentors in a college. So I was very privileged to be in Vidyalankar. At that time, Vidyalankar was one of the uh, best in terms of faculty. So I need not to join any kind of a classes or something, and yeah, ma'am was one of the mentor for me, and I did my industrial training in BRC, that was in signal processing, working with the LabVIEW and all. So not conventional kind of industrial training, but ma'am were very supportive in that as well. So yeah, thank you, ma'am. Thank you.
Thank you so much, sir, for sharing your amazing experience and joining us for today's session. I would request all the participants to please switch on your cameras for a quick photograph.
There is something wrong with my camera drivers, so I did not able to.
Hello, sir. Could you please stop sharing the screen?
Rituja,
Thank you so much, all of you.
thank you so much. Lastly, we will be continuing with this session on Wednesday, 8th September from 6:30 p.m. onwards. So, hoping to see you all there. Please fill up the feedback link. The link will be open for a limited period only, and complete the assignment before 7th September, which the link for the assignment will be open till 10 p.m. only. And lastly, I would like to thank all the faculty members and the participants for being a part of this event today. Hoping to see you all soon. Thank you so much. Thank you everyone. You can now leave the session.
Requesting everyone to please fill the feedback form and the